Okay, so this room, for those of you who are sticking around for the next presentation, is going to be full of interdisciplinary projects all day, or projects that were so large that they could not accommodate in a 20-minute presentation. And obviously, I'm guessing most of you in this room know how much work these guys have put into this. It takes more than 20 minutes to present this. So, what I would like you all to do as you're watching the presentation is pay attention to this evaluation form, because we use this A, for their grade, and B, as part of our accreditation validation process for assessing our seniors. So if you could give them your full attention, take it away, guys. Okay.
Yep. Hold on, guys. All right. So, good afternoon. I'm Peter Soretta. This is Justin Tussey, Mike Bruno, and Alexander Knott, and we're SAE Senior Design. So on this first slide, what you'll see is the finished product. And we want to take you through a journey on how we got from start to finish where we're at here. So in coming to this problem, we had to cover these aspects of the agenda: the design process, the manufacturing, the challenges and difficulties, the lessons we learned along the way, and the acknowledgments of all of our sponsors like Automotive Trade and Fred Farm. So, when coming to this whole new field of engineering for us, we realized that we had to actually learn a whole new dynamics, pretty much, and it's a dynamics called vehicle dynamics. So we came to this question and we said, what is the optimum suspension and chassis design for a Formula Series race car? And we found 4 parameters that we wanted to maximize, mainly being grip, acceleration, velocity, and cornering force, while minimizing body roll and loss of traction. So the big question we want to answer today is, how do you design a Formula SAE series vehicle? The answer is, you work from the outside to the inside. You begin with your wheel package, your tires, you establish the parameters you need to work from there. Then you establish your suspension points, while simultaneously establishing your steering points. And then you connect everything by the chassis. In the racing industry, the chassis is known as the big bracket that holds everything together. It's where all your load gets dissipated. And what we noticed about this process was how iterative it was. We probably went through 6 entire overhauls of our car. And every time we started beating the learning curve, we started getting more efficient, and we started getting better results. You'll see up there a picture of what we started with. And what we wanted to start with was selecting the track width and the wheelbase. So the track width is your lateral direction between the centers of both tires, right? And then your wheelbase is front to back, so it's your longitudinal center tire distance. We chose a track width of 52 after iterating initially from 60 inches, because 60 is wider, right? That was the widest track width that we could have, and we realized that we might hit a cone on a road course in Michigan if we keep it that wide. The reason that we actually had it at 60 initially, though, is because ideally you want to maximize your lateral weight distribution. In other words, you want to minimize your roll in order to avoid an overturn or high forces in your suspension components. And our wheelbase we chose to be 64 inches. Talking about the chassis constraints that drove its design, we had governing FSAE rules. You can see in this picture there's various cutouts of steel. One of them, you can see 3 circles right there at the top. Those actually make up what's called the 95th percentile male. So what that is in the FSA rules, it's a template for an average male, so you can get your ergonomics for the driver mapped out. You also see this front bulkhead steering clearance template. And then you can see Justin Tussey over there. He's working the anti-gravity steering wheel. But we did stuff like this. Average male. Above average. Yeah, above average. Jolly Green Giant average. And so we actually sat in a Formula V car to map out our steering and our driver ergonomics. You know, we had to know, okay, how are we going to make our driver the most comfortable possible so he can maximize his efficiency in the road course? Because we don't want him being really uncomfortable trying to deal with that and also trying to stay focused on the road course. So I'm going to hand it over to Justin to go over the wheel package assembly.
Yeah, sure. So once you've established your outer limits, or your centers between your lateral and longitudinal centers, you can start working on your wheel assembly so you can figure out where you'll be able to put your outboard points for your suspension. So when you approach the Formula SAE design, you're basically limited to two choices, either a 10-inch wheel or a 13-inch wheel. We chose to go with the 13-inch wheel because it allowed us, gave us a greater room for packaging. It let us put a larger brake rotor in there, which would give us better stopping power, and just made it easier overall to design inside this area versus if we were in a 10-inch circumference or diameter. It's difficult for even experienced teams to package their wheels into 10-inch. So we went with 13, which gave us an inside diameter of 12.75, so we knew how much area we had to work with on the inside. And then we had to work back a little bit further. Oh, I'm sorry. Actually, this is the wheel that we chose. So it's the Kaiser center lock 1 with a 13-inch diameter, 8-inch tread width. That's the weight. And it's a 3-piece modular system. So you have your outer rim, then you have your wheel center, and then you have your inner rim, and they all bolt together. And it's made out of 6061 heat-treated forged aluminum. And the heat treatment makes the material stronger. The tire that we chose was a Hoosier tire. They provide a Formula SAE discount, and they're also present at the competition, so it was good to go with them. They have pretty good Formula SAE support. We went with an 8-inch tread width, which is the maximum that you can choose. And the reason we went with the maximum tread width is our preliminary research showed that the most significant factor in driving a car's performance is the tire grip. And generally, the wider the tire, the more grip you have. So that's why we went with the 8-inch. One possible downside that we may see when we actually start tuning the car is that the larger you make the tire, the longer it takes to heat up. And tires don't operate as efficiently until they reach their operating temperature. But we really had no empirical data to go off of. So we just went with the largest one, and we'll see how that works. But they may want to step it down in the future. The wheel bearing that the wheel rotates on is a SKF double row angular contact ball bearing. What this does, the reason we went with the double row angular contact bearing is it has the 2 ball bearings, which allows for radial and axial loading. So normally teams will have 2 bearings with a spacer in between it. If you use a double angular contact, double row, you can get away with 1 bearing, so it reduces your packaging, your weight. So once we had our wheel picked out, we were able to work back a little bit and figure out what our inboard distance was, which allowed us to work it on our wheel hubs. This is the custom designed wheel hub that we made. It's also made out of 6061 heat-treated aluminum. And if you can see the mounting holes here, we're going to put a Galfer brake rotor, and it has a safety factor of 2.5. And these are the holes for the drive pins to transmit the torque to the Kaiser wheel. The hub goes inside the bearing, and the bearing is pressed into this structure called the wheel upright. The wheel upright is the bracket that connects your upper control arm to your lower control arm and your steering arm in the front, and it holds your brake caliper fixed. So this is your brake tab. It's also made out of 6061 heat-treated aluminum, and it has a safety factor of 2.5. The front braking system, we went with the Wilwood GP320, which is a really powerful 4-piston brake caliper. It provides 650 pounds of clamping force. And the brake rotor that we picked out to go with it is the Galfer floating brake rotor 504. What's interesting about a floating rotor, while I'm explaining what a floating rotor is, a floating rotor is, it's actually 2 pieces of material. You have an outer ring here, and then you see these larger circles. That's actually a joint, and then there's an inner ring right here. So it's actually 2 pieces clamped together, and the joint is actually a little loose, and what that does is it allows for the thermal expansion of the brake rotor as it heats up, so it doesn't warp. If you have a fixed brake rotor, which is a solid piece of whatever material you choose, steel or something, if you just make it out of 1 piece of steel, as it heats up, it's going to bend and reduce performance and increase vibrations and shatter into your brake system. So It's pretty important that we picked out a floating brake rotor. That was a key feature that we needed. Actually, let me go back on. The Willwood GP320 is a 4-piston cylinder, which gives it a lot more power, or stopping power, because when you're in a car and you're braking, you're going to have longitudinal weight transfer. So it's going to shift to the front, and you're going to need more. You're going to have more weight on your front tires, so you're going to need more braking force. Your rear tires are going to lift up a little bit. So that's why we have 4 pistons in the front, and in the rear we have a Willwood PS1, which is two pistons. So it's a much smaller brake. You see a less braking force, goes from 650 to 350. The area goes down significantly, and the Galva brake rotor that we picked out is the floating 037. And I'm going to hand off to Al, who's going to talk about the suspension assembly.